Now let's see how we implement the CA method using Colab. So first, we still use our input example where the resolution is 0.001 and Tmax is 3. And then the demand rate is piecewise constant, where the first is 100, second part is 80, third part is 50. So first, we will apply our CA method to solve the optimum headway function piecewisely using our formula. So here, remember, we use this d indicates d prime. Okay, you can see after we apply our CA method, we get our optimum headway function at what we derived last class, 0.615. The second piece is 7, and third piece 0.869. So we can first apply our estimation as we just introduced. Our number of shipments can be approximated by H inverse. So here we just put H inverse dt in a list, and then we take the integral, numerical integral, and then take the integer from the integral. So in this specific case, we estimate our n hat to be 4. And then we can also estimate our total cost, which can also be easily calculated based on the parameter and then d prime. And then we calculate the numerical integral. And then in this special case, our optimum solution is 1599. Now let's calculate the CA solution from our optimum headway function to get our real solution where the headway can be implemented into schedule. So that is our 45-degree method. So let's see how can we achieve this. So our logic is pretty simple. If we have some optimum h function, what we do is we draw a 45-degree line, and then we want to find out a point that this area of the square should be similar to the area under h. So to achieve this, we will record two areas. One is the area under h function, and then another is the area of the square. So as we can see, we enumerate from the beginning to the end. And then in the beginning, the square is pretty small, and then the area under h should be large. And then as the square grows slowly, you can see the area under the headway is higher and higher. Actually, if the square is too large, then the area under the square is much larger than the area under the optimal headway curve. So we will just find the turning point where the square area first oversees the area under the optimum headway function. So we just do enumeration from a start point, gradually increase that until we find out the area of the square suddenly is beyond the area under the optimum h curve. And then we just record this point, which is our shipment schedule time. So after we implement this, we plug in t equals to 0 as a starting point. After we do this 45-degree line method, we can generate 0.616, which are next schedule. So T1 is 0.616. We put 0.616 here, and then we can get T2. So T2 will be 1.262. So we can keep doing this until we find all the schedules. Remember that the number of shipments is 4 from our estimated n hat. And then we repeat the 45-degree method from the beginning to the end. And then we can have all the schedules from T0, T1, T2 until Tmax. So we just use the estimator for the number of shipments as the input, and then we keep doing our one-step function for the 45-degree line method, and we can get all the schedule. In our example, the number of shipment is 4, so we can ship at t equals to 0, t equals to 0.616, t equals to 1.262, and then the last shipment is 1.951. And then after we determine a schedule, recall that this is a feasible schedule. So we can just implement this schedule and see what the total cost is. Remember that when we estimate our total cost, we can use the version for the headway function, which is a step function to estimate the total cost. So here, HST should equals to 0.616 when t greater than 0 and smaller than 0.616, and then equals to 1.262, and then 1.951, and finally 1.049. So 1.049 is 3 minus 1.951. And then we plug this exact schedule in, and then we can calculate the total cost. So after we get the calculation for the total cost, we can compare it with our solution from dynamic programming. In the previous lecture, we have calculated the solution to the problem using dynamic programming with a resolution of 0.005 as this schedule. So we calculate our CA schedule. This is our CA schedule. And then this is our calculation from dynamic programming. And then this is our estimated CA cost. So you can see our schedule for this problem. Using CA method, we give 1609, and then use the dynamic programming is a slightly better, and then our estimation actually is very close to the solution. But note that this is just estimation, so there may be errors, which makes sense. So you can see our CA solution is pretty good. So now let's do sensitivity check, where we want to evaluate how the impact of the slow varying to our CA solution. This is pretty interesting. So here, to design a slow varying input, we consider a sinusoidal function as our demand rate. Here, we just vary the amplitude for the input demand over the time. So you can see when the variation becomes large, actually it's kind of very faster. When the trend of the demand rate becomes smoother, then the varying is relatively slow. So we use the vector variation to indicate how fast it varies. When it equals to 0, that indicates there's no change on the input demand rate. When the variation is 1, then the smallest demand rate will be 0.